cannot find. All right, okay, I get this one. Good. Good morning once again. Let me start. Before the last lecture of this course of quantum transport, usually by this time I have last lecture. I don't want to intrude students with the lectures in June, but anyway, we were not there yet. I will talk today about tunneling in electromagnetic environment, and in a week we will have a lecture about coherence, about dissipation, the concluding lecture of this course. Good. Tunneling in electromagnetic environment. What will I talk about? I will try to understand the relation crossover between two limiting cases we have studied: scattering theory and Coulomb blockade. I will do this, I'm able to do this only for electron tunneling. And the phenomenon which I reveal is called Dynamical Coulomb blockade. It's kind of incomplete Coulomb blockade, which comes because the electron which tunnels interacts with environment, and if interacts very weakly, you just have scattering. If it interacts strongly, we have Coulomb blockade, and we are able to describe intermediate case of coupling, actually in quite some detail. In order to understand this, we have to go through all these topics, and actually we can quantize electric circuits, and we will be able to associate the coupling of electron with environment supplied by electric circuit. We can characterize this coupling in terms of impedance of the environment. Right, then we apply these concepts to a couple of different setups, various kinds of tunneling. We will talk about tunneling in charge qubit. We will talk about tunneling of Cooper pairs, which is Josephson effect that we have considered. We will talk about tunneling of the phase, which we have also mentioned briefly once, macroscopic tunneling in Josephson potential. Right, and we can kind of describe all this phenomena on sort of equal footing in working the concept of electromagnetic environment. So this is a plan for today. Right, so let me formulate a problem. Let me make a setup and understand two limiting cases in this setup. First of all, we have tunneling. we have a possibility of electron transfer between two leads. Right. One lead is just first, another lead is arranged like this. There is a capacitance, and there is a connector which connects this piece of the lead to us again. Two limiting cases. If this conductance, connecting conductance, is large, we can set it to infinity. Then what we will have is just two leads, both east. And then we know how to describe transport, it's just elastic tunneling, something which we have discussed in lecture number 1, 2, and in several lectures afterwards. If this conductance is small, okay, then just let's put it to 0, and there is no connection whatsoever. What we will have there is a channeling to Coulomb island, which means that tunneling cannot proceed at small voltages, at small energy differences. No tunneling would occur till certain voltage. All right, let me remind you why. Let me consider energy diagrams of this tunneling. So, large conductance. Here there are field states, and one of the electrons can tunnel to another. So there's energy axis. If we forgotten, that's energy axis. And I consider transitions from one lead to another lead. Green is just tunnel barrier. Good. What I wanted to say is that the energy of outgoing electron after tunneling is precisely the same as the energy of incoming electron. In the limit of small conductance, let's see what we have. The electron which comes to here to charge the system. That costs charge and energy, EC. That's why it has to go lower, in energy. And that is only possible if the voltage applied, oh, here I have it. If the voltage applied is bigger than corresponding charge and energy, exceeds Coulomb blockade threshold. Right. And the problem which I want to address, what is there in between? What will happen if I just, for instance, vary experimentally these conductance and study tunneling through this contact? Right, so let me explain in few words what will be there in between, and then we will discuss why it's so and how to derive this. In between, the electron tunneling will be characterized by this function, P of E. P stands for probability, E stands for energy. And this function gives probability to have energy loss E. So an electron, which is going to tunnel, can give different amounts of energy to the surrounding system, to the environment, to electromagnetic modes in this additional connector. So, for two limiting cases, the energy loss is not stochastic. It's either elastic tunneling and energy loss is zero, or this is Coulomb blockade and energy loss is charging energy. But in between, it's just a function of energy. Let me try to sketch it, something like that. Right. Why is it so? We will discuss a little bit later. Let me now notice that if we know this function, there's no problem to compute tunneling rate, to compute the current through the junction. How do I do this? E. Tunneling counts about all energies of incoming electron, and this state has to be filled. There must be a place for outgoing electron at energy E prime. And the difference between these two energies, E and E prime, is just energy loss. So probability comes handy here. Oh, other question. Oh, yeah, sorry, I missed the questions. How can I get questions? It's always, yeah. How can P of E be a distribution if it is equal to a delta function? Right, it's a very simple distribution when there's no spread. It's always the same value. It is a stochastic process, which always gives you the same value. In this case, it is a distribution. Anyways, we are talking about limiting cases. It means that if we deviate just a little bit from elastic conditions, there will be some function, but this function will be close to delta function at zero. The same about Coulomb blockade. Yeah, for instance, in Coulomb blockade limits, it could become a function like this, very close to delta function. Yeah, what must be always one, it's good property to know its probability. So eventually integral over energy for this probability must be one, right? there must be some energy loss, either zero or non-zero, whatever. So in total integral over this distribution must be like. Good. Let us go and let us understand how this concept of probability comes about. And simultaneously, we do something to characterize this function as well. So let me consider a very simple example of the environment. So there is a tunnel junction, electrons go through this tunnel junction, and there's capacitor, but instead of resistor, we will have inductance, right? Capacitor plus inductor gives us oscillator, single mode oscillator, which can oscillate at this particular frequency. Then what can happen? Electron, when tunneling, can give its energy to this oscillator. Or cannot. It's a probability. So when tunneling, this is stochastic process, this several with many possible outcomes. In any case, the electron has tunneled, exciting certain number of quanta, which is different from case to case. Right? That's why this function P of P, it is made from delta functional peaks and coefficients just give the probabilities to excite certain number of quanta. Right. Then let me describe a formula which I don't want to derive now. We have derived it in the course of advanced quantum mechanics. In fact, this formula gives the probability to excite a certain number of quanta in terms of this number, and let us see a parameter. Oh, there has to be k here, sorry. A parameter. This parameter is the ratio of charging energy associated with this capacitor and well, frequency of the oscillations. The resulting distribution is eventually Poisson distribution. I believe we shortly discuss the properties of Poisson distribution. It comes in different areas of physics. I believe I will have examples next page. It comes about in different areas of physics. What I also want to mention that this parameter gives the average number of quanta that can be excited in the course of this process. Too much? Let's look at the limits. Right. So first, although I don't want to write down the derivation, let us understand the essential physics, what is going on. Then no electron, in the beginning, the oscillator is in its ground state. Then electron goes to another lead, it shifts the position of this oscillator. Well, the coordinate here is eventually charge at the capacitor. Right? So it will charge the capacitor, and that means that oscillator is excited because, well, its position doesn't change, but the equilibrium position has changed, so it is excited. Right. So what does it mean? If we quantize this oscillator, there will be a set of wave functions corresponding to different states. While initial wave function of the oscillator is somewhere here. Okay? And probabilities are given by overlaps. Let me call this function psi. And let me call this function psi with numbers. Probabilities are given by overlaps of these functions. Right. To compute that, one has to basically take wave functions of the oscillator in certain representation and do this in a product of two wave functions. Right. Let us look at this Poisson distribution at different values of average number of quanta emitted. Okay, here it's small, and the highest probability is to emit no quanta. There is some probability to emit one, and in principle there are probabilities to emit any number, but they're very small. Let's face n. Good. So average n is somewhere here. The probability, still found out. So we will have increase of probability, and the shift. In any way, the average of this distribution should correspond to this. Let me look at n to the 4. Here it is the average. And the distribution is already reasonably close to Gaussian function centered at 4. Right? If we increase n bar even further, it's a property of Poisson distribution. It will be centered and an average, and its spread will be given by square root of average n. Properties of Poisson distribution. Right, so I believe I explained how does it come about. I believe I give you the notion what happens to Poisson distribution at small and large value of this parameter. Right, let us now use this value of P of E to describe the current. To understand the curves of the tunnel junction which is connected to an oscillator. Right, first I look at differential conductance of the junction. Why it is convenient to look at. Let me recall this picture with voltage strip. So the current is contributed by electrons in the whole strip. And if I change the voltage, I will change energy strip like this. So the change will be due to tunneling of electrons at certain energy. Right? So the differential conductance is given by electrons which are there in the strip. So they have certain energy, and the and if we look at how many quanta they can emit, the number of quanta which they can emit is restricted by the width of energy strip by itself. Right. So if this energy strip is smaller than h omega naught, the electrons cannot eventually emit anything. And the current is proportional to probability P of 0. That we can see it just for different values of an average corresponding to the plots I showed, these plots. Right, then what happens? Look, when voltage approaches this threshold, h omega naught, there is a opportunity, let me say, opportunity to emit another, to emit one quantum. So the probability which defines conductance becomes P naught plus P1. Then here it becomes plus P2. And finally, this infinite number of terms amounts to 1. So the conductance is the conductance in the absence of coupling, somewhere over here at high voltage, and it increases step by step when voltage approaches integer number of h omega. Good. This is a differential conductance, what I want to show on the right is the current. There are kind of spectacular steps in this conductance. One clearly sees that they become cusps in this curve. So changes derivative jumps. You can, for instance, see cusp for B. But if you just plot it, you hardly see these cups. What you see is overall behavior of the curves. And we immediately see that curve A is reasonably close to linear dependence of conductance, while curve C is reasonably close to another limit of Coulomb blockade when there's no current up to certain threshold. And then, as we know from Coulomb blockade theory, it increases linearly above the threshold. Good. That's a message. Coupling to the environment can be different. If the coupling is small, the IV curve is almost linear. If the coupling is strong, it approaches Coulomb blockade limit. All right, that we have understood for an oscillator, and I want you to give you a crash course on a subject which is usually considered to be quite advanced. It's about quantizations of dissipative systems. Since we are talking about electric circuit, it's dissipative circuits. Right. So I don't want to go to whatever physical mathematical details. I just provide you general hints how we can deal with that. Let's begin with this oscillator. Let us draw the real part of its impedance. What's impedance? You have a current source, you have voltage response, and this is the coefficient between its impedance. Right. And you concentrate on real part of the impedance, which gives you dissipation. So for ideal oscillator, the real part of the impedance just delta functions. That's what we see. That's what we remember. Yeah, it just means that oscillator can absorb only quantized energy. Good. Let us now change the oscillator a bit. Let us now add a small resistance to this oscillator. Then from circuit theory, we know what happens. This delta function will acquire some finite width. The relation of the width to frequency would be quality factor of the inverse quality factor of the oscillator. But anyway, we will have a peak of finite width characterized by impedance. And let us now assume that only impedance of the circuit matters. So it could contain many other capacitances, resistances, inductances, anything. But what matters is the whole impedance of the circuit. Then eventually we can combine, we can build up this impedance by combining many extended peaks like this. We can model an impedance with oscillators like this. Okay, more oscillators we take, the more oscillators we take, the more accurate the modeling will be. But the message is that dissipative circuit can be seen as a large set of single mode oscillators. And we can quantize an oscillator. We have quantized it during your first encounter with quantum mechanics, which means that we can now quantize dissipative circuits, quantizing every oscillator in there. Good. So how did it go? This crash course. Are there any questions about this? It's kind of rather important reasoning which I explained to you. No questions. All right. So there's a way to quantize dissipative circuits. So now we can replace a single mode oscillator with big set of oscillators. And then we will consider each oscillator separately and look at the energy loss to all possible oscillators. Let's see. Okay, differential. Good. This is the result. Perhaps it's difficult to digest this form from the answer from what I said to you, but believe me, I said more in the course of advanced quantum mechanics. Believe me, that works. So let us understand the form of the answer. This P of E appears to be Fourier transform of some exponential function of time. This exponential function of time, which goes to exponent, is in its own turn related to the impedance, to real part of the impedance. I don't put real part explicitly. So if one knows impedance, it's frequency dependence. One can compute this function J. and put it here. This J are written in a form which shows that this is a sum of contributions of individual oscillators. And each oscillators are labeled with M. And there is a certain average of quantum a tunneling particle can excite in each oscillator. And they all end up in this expression. Good. Sure, we know how to compute, in principle, P of E or a general linear circuit, dissipative circuit. Let me sketch possible answers. It turns out that depending on the properties of this impedance, P of E can be of two different sorts. It is important to talk about probability of tunneling without energy loss. And there are two types of answers. For first type of answer, there is no opportunity to tunnel without energy loss. No elastic tunneling whatsoever. Second time looks more like the case we have considered, the case of peak coupling. So there is a delta peak at 0. There's finite probability to tunnel without energy loss. And there's also some probability to tunnel with energy loss. Right. There are two different cases. From the other hand, impedance can be changed continuously, which means that there has to be a borderline between these two cases in the space of impedance. And it happens that this borderline is set just by the value of impedance resistance of the circuit. So let us now concentrate on this borderline because it's also most relevant model. It corresponds to finite impedance at 0 frequency. Sure, it's called ohmic dissipation. And for ohmic dissipation P of E becomes power law with exponent, which does depend on actual value of the resistance. To understand what is going on, how could it be, and how exponent is actually, and how to reconcile this power law with the fact that integral over P of E must be 0. Let me just look at the left plot. I have to zoom in. Last time my computer crashed because of that. No, it doesn't. Hopefully. Good. So we see now different curves, and the horizontal and the vertical axis is P of E, and the horizontal axis is energy. Right. If the coupling to the environment is weak, resistance is small in units of resistance quantum. Let us see where we are then. We are here. Curve A. So you see it grows at zero energy, and in fact it kind of becomes a delta peak at zero energy if you put resistance to zero. That's what we expect for elastic tunneling. Then the exponent changes. So for curve B, the exponent is 0. It's not negative anymore. It's 0. Then it becomes 1. For curve D, it's 2. For curve E, well, I believe it's like 20. So there are sharp exponents, which means that P of E is almost 0. Right? Integral of P of E must be 1. That's, for instance, for curve E. That amounts to a peak like this. So we've now almost we don't have almost any probability at low energies, but well, we have a probability, and this is centered eventually at charging energy. How can the probability be larger than 1? Because we are talking about probability per energy interval. This is our definition of, let's see, I need to change to a pen. This is our definition of the probability. All right. So in fact, P of E has a dimension. It has a dimension of inverse energy, and it can be anything. Right? What must be fulfilled, as I said, the integral of this probability must be 1. And here it is satisfied by this. Fine. Yeah, anytime I'm talking probability of E, it is a probability density, right? When I talk about discrete modes like an oscillator, then I have a probability for each mode, which means that this probability density is a sequence of delta functional peaks. Right. I want, before the break, I want to show you the right plot, which is actually the same plot, but now all these curves are plotted in double log scale. And you remember in double log scale, any power law becomes a straight line. So that's what I promised. All this very good. I'm back. let me go on with this lecture. Let me recall that we just look at the probability of energy loss, P of E function, in the case of resistor, ohmic case, and we basically understand that it's power law at low energies and some function at higher energies, which is at big resistances has a form of Gaussian peak. Let us apply it to tunneling. Let us look at tunneling current under these circumstances. Right. So what I want to look at are IV curves of a junction which is shunted to the resistor. Just a original problem which we had first slide. Right. As in the case of special environment with a single mode, let me look first at differential conductance. Here is a plot of differential conductance. And the different curves correspond to different values of this parameter, basically different values of the resistance in terms of conductance function. So we see a rather sharp crossover from the situation at low conductance, when conductance deviates from 1, but not very significantly, to the case of very large resistance. I'm talking about low resistance for red curve, large resistance for yellow curve. Let me make it yellow. Yeah, here it is. So yellow curve is almost 0, and then it approaches 1 at some stage, all around a voltage of the order of charging energy. Good. So what can I say? In fact, it looks a bit similar to the curves I showed to you for a single mode environment, but without this sharp jumps. Just smoothed curve, right? And that becomes especially relevant if you look at the current, if we integrate all this differential conductance or voltage, if you get current, then again we see that there are two types of the curves: low impedance limit, like red and green curve in this plot. They don't differ much from linear slope, while in the limit of high resistance, high impedance, the curves approach this law, Coulomb blockade, and then linear slope. Right. The fact that power law dependence, the fact that P of E at small energies is a power law is manifested in the current like this. It is, we didn't talk about temperature. This is for voltage, which is bigger than temperature. But there is a strange anomalous power law between current and voltage in this case. Good. So at this moment, we have solved the original problem we have formulated in the first slide. We understand the tunneling of the curve in the presence of external circuit, in the presence of external resistor with resistor R. Then, as I promised, I take this knowledge. We have gotten knowledge about P of E, this concept, and I will apply this concept to various situations, various kinds of tunneling. Right. Sir, let me first modify it in a rather obvious way. So I don't want to, I want to have a charge. I don't want to tunnel it between two leads. I want to keep it at two islands. There is a tunneling between two islands, and there's various capacitances associated with these islands. Right? But there's also dissipative environment, which I represent with this resistor. Sir, this is a model of charge qubit. I can talk about charge, which is either in this island or in this island, and that corresponds to double well potential. So there is some energy shift between the walls of this potential. And there's tunneling. I guess I need to take another color. There's tunneling between potential wells, which corresponds to this tunnel junction. Right. Now I want to find the place for P of E here. To this end, I would like to consider the tunneling. I would like to consider an electron in the excited state of this 2-well potential. It will go to lower state, which is separated by energy bias epsilon. And the only way to go is to disperse this energy to the environment. That's how energy loss in the course of tunneling comes here. So the rate of decay will be proportional to some tunneling amplitude. Actual value is not very important. What is more important is the dependence on energy bias, which is given by P of E function. Good. Now let us understand what kind of P of E function we need to use. If one looks at the effective impedance, just electrically, between these two curves, between these 2 points, right? Impedance is 2-point function. One can take 2 points in the circuit that defines your impedance. 2 contacts, yeah? And the impedance for these 2 things, in order to compute it, you need to consider all these capacitances, division of voltage between all these capacitances to come up with this expression. So this is resistance of this external resistor times a factor which which depends on capacitances. Right. So now we can apply our knowledge of P of E. The only problem one needs to modify the resistor, the resistance which is in this formula to modify it by this factor. Right. So what we can now say about charge qubit in the environment. Interestingly enough, these qubits can be in two phases, separated by a phase transition, which is usually called Schmidt phase transition. Without going into details, let me understand how to pinpoint this transition. Let us use the expression for P of I we have. Okay, what I have here is impedance. Impedance is resistance times this capacitive factor. Right. So the exponent depends on the impedance. From this, we can estimate decay rate. That has certain energy dependence. Now it's a decay rate, and what I want to do it, as we did already several times in this course, I want to compare it with energy itself. Right? If this rate is smaller than energy, it's kind of okay, it's usual situation. We really have a level which is not too much bloated. We have a level which looks like usual quantum level. And in opposite limits, at low energies, the width of the level will become comparable with the distance of the level. And yeah, it is not what we expect. There will be no level. In fact, it appears to be that in this case, tunneling between the wells is quenched, and there is no the electron is localized on one of the wells. While in opposite case, it's more like quantum mechanics suggests us, it is delocalized between two quantum. So the transition occurs from this consideration when gamma divided by epsilon is constant. And if I use this power exponent, we pinpoint the impedance at which the transition occurs. Good. So we apply the same concept to the qubit rather than to the electron tunneling between the leads. We got yet another interesting answer using the same concept of P of T. Good. Let me look at yet another variation of tunneling. Let us recall what we know about Josephson junction. Okay, Josephson junction. We remember that it's characterized by energy or term in the Hamiltonian, which depends on phi, on the size. And if we present this term in Church representation, these cosine phi's will be equivalent to the exponents, which are components of cosine. To remind you, cosine is the sum of two exponents. These exponents will correspond to Cooper pair transfers through the junction, Cooper pair tunneling. All right, we record that. Let me now consider the following setup. I take Josephson junction. I put a resistor next to it, and I will also set a voltage source. What kind of Hamiltonian do I have? I would like to have Hamiltonian in terms of charge, which goes through the Josephson junction. Let me first take into account a term which comes from source voltage. Voltage makes it energetically favorable for Cooper pair to channel. Right, so the states with different n, they in fact form a ladder. Josephson energy provides tunneling between the steps of this ladder. Each tunneling must be accompanied by energy loss, which is in this case written here, 2 EV. Two comes from the fact that it's Cooper pair two charges. Right, that sets the Hamiltonian. Here, all information about the resistance I choose to put into an operator which presents electromagnetic modes and which is in fact equivalent to voltage fluctuations. That gives the opportunity. Let's talk about opportunities, although it's up to, how would I say, to human way to imagine an electron. In this case, Cooper pairs are tunnels. So it has an opportunity to dispose the energy to EV into the environment and thereby go step by step where the voltage tells it to the low energies. All right, sir, it would be enough to consider just each step in this ladder a single tunnel in which occurs. Right. And again, this is yet another case of decay. There's a qubit, there's a tunnel amplitude. So we can eventually use the formula which we have for a qubit for this situation. So the rate of this tunneling will be proportional to P of E at certain voltage at voltage 2E. Right. From the other hand, each jumps is Cooper pair tunneling, so the rate is rate eventually determines the current. The current through Josephson junction. And here's the plot. I don't want to zoom on it because I have already. Eventually, it's just the same plot I used shortly before the break to discuss the properties of P of E. Well, there is a simple, the current, the rate is just proportional to P. Good, so it's the same plot. And one can see distinct behaviors of the current with respect to voltage. Namely, if resistance is small, it kind of grows up at small voltage. And in fact, at very small resistances, it would form a peak. This peak will correspond to supercurrent at 0 voltage. Again, the probability to tunnel without energy loss will give us supercurrent coherent transfer. Although, let me perhaps start this. The process which I consider is not supercurrent. It is accompanied with by dissipation, and there's also voltage source. Right? If voltage is 0, I will have all these steps perfectly aligned. Right? And what does it mean? It means that tunneling would create a delocalized state, kind of blockade for this in this space. Delocalized in charge, it also means localized in phase. So there will be a state with certain phase. But in order to do this, one has to depart from this situation and set voltage to 0. Oh, I go to the wrong direction. Good. Another detail which I want to mention, since we have double charge, the impedance which enters expression for Cooper pair P of E is eventually 4 times bigger than the impedance for electrons. Good. This is tunneling of Cooper pairs. Let us now understand how Schmidt transition is manifested in Josephson junction. So let me try to understand it in terms of localization and oh, there's a misprint in this transparency. In terms of localization and delocalization in charge or phase space. All right, so if there is a supercurrent, it means that the phase at Josephson junction is well defined. That supercurrent is just a function of phase. If you would let this phase fluctuate, supercurrent will vanish. And in this situation, the charge at Josephson junction is undefined. Remember, we talked about this when we talked about Cooper pair box, about Josephson junction. Inverse situation is there absence of supercurrent. Just Josephson junction, if you put sufficiently big resistor in series, will not be superconducting anymore. Right? That would correspond to IV curves like this. So when this transition will happen, this transition will happen at the value associated with the Schmidt transition. And in order to look at it, one has to rewrite this, implement this ratio between rate and energy. When it goes to constant, Schmidt transition will happen. Again, let me sketch IV curves before and after the transition. So that orange one corresponds to well-developed supercurrents at low voltages will have finite currents. And the rises curve at the transition. And there is a V curve somewhere at very large resistances, and there will be no current. So the Johnson junction, despite the fact that it's superconducting, wise, it's Cooper pair will attempt to tunnel, but interaction with the environment is too strong. So no chance. Only if you apply sufficient voltage, it can penetrate this energy barrier, it can tunnel. Good. So that was a description of Schmidt transition and Josephson junction. In the end of the lecture, let me discuss yet another kind of tunneling. Let me talk about tunneling of the phase. But since superconducting phase is related to magnetic flux, they frequently call it flux tunneling. Let me remind you the washboard potential for Josephson junction. So its slope is determined by current. And if you consider Josephson junction as classical particle, it can be situated in any of these minima. Now let's recall it as quantum. So there will be tunneling between these two minima. And if, as we can see, we are back to ladder situation. But in this case, the states are not charge states. Quite opposite. There are states with different phase separated by 2 pi, phase shifts. Good. But ladder, let us try to describe it in a way similar to what I had before. So we have tunneling between neighboring steps of the ladder. We have bias, which gives a slope to the ladder. That is eventually the energy associated with the current, which one has to overcome. I'm just trying to write this formula. Yeah, here we are. And the rest electromagnetic environment which is in this case are represent as fluctuations on this current. Again, the logics that in the course of this tunneling, one has to dispose energy into the environment, otherwise it will not go. And depending on coupling stance, that can lead to two different situations, to either localization or the absence of localization in the limit of small slopes of the ledger. In this case, in the limit of low voltage. But what is kind of interesting in this picture, since charge and phase are dual variables, very much like momentum and coordinate are dual quantum mechanical variables for a particle. The roles of current and voltage, impedance and admittance. So impedance is kind of frequency dependent resistance. Admittance is frequency dependent conductance. They are changed with respect for these two situations, right? To do so, let me have these Hamiltonians next to each other. So there's a current bias junction, and there's a tunneling of phase, and gives you different phase states. There's voltage bias junction, and here gives you different charge states. Here the slope is defined by current. Here it is defined by voltage. Environment is either fluctuations of current or fluctuations of voltage. So in fact, P of E for this system is determined by admittance rather than impedance, right? That's what one has to do. The impedance which we had in P of E function, one must replace by admittance. Good. This nature, there's a difference between two kinds of tunneling. They are quite different, tunneling in different variables. Summing up all that, let us see. There are two limits. The limit of low impedance and the limit of high impedance. In the limit of low impedance, phase is a good variable, has a very well defined value. Phase is localized. So we have just some currents at voltage bias junction, and the localization here. So charge is delocalized. And in opposite limit of high impedance, the phase is delocalized. It is charge which is localized. Josephson junction is not superconducting anymore. And these two limits are separated, as we discussed, by Schmidt transmission. Good. I guess I have done with all the stuff. Just let me mention in the end of this topic that we have just only touched the whole world of very interesting processes which are related to interaction of electrons or qubits with in environment of different kinds. We've been looking at the electromagnetic environments, but if you combine it with electron motion, one also can see how electrons can escape. For instance, blockade. One can study also experimentally lateral liquids, electrons in one-dimensional nanowires, for instance. There's also environment which is made by fermions, which give rise to Coulomb effect, which one can see in quantum dots, transport quantum dots. It results in Fermi-edge singularities, which is also observed experimentally. There's also a problem how to describe this interaction for transmissive junctions, and that all these topics we don't even touch. There is, however, an important topic that which we ought to touch, which we ought to discuss, because it's kind of gives ultimate of justification of why we can regard electrons as quantum waves, why we can regard qubits as quantum systems. That's all about the assumptions, about decoherence and relaxation in these setups. And that will be the topic of the next lecture. So with this, I wish to thank you for your attention. To remind, there will be yet another lecture in a week. I hate to give lectures in June, but well, there is whatever so that will happen. Right. So thank you for your attention and see you next time. And I shall apologize for the fact that I announced this, that I sent Zoom link too late. So thank you for all of them who were attentive enough to catch it in the morning. Bye.